Hello, everybody. Welcome to 5.3, Conditional Probability and Independence. Uh, so you probably don't know what conditional probability is, so it's probably good to define it to start off. Conditional probability is the probability that one event happens given that the other event is already known to have happened. That might sound a little goofy, but really all it's saying is in these problems you're going to be told this is happening. If we know this is happening, what's the probability of another thing happening? Okay, because a lot of times if you know something's going to happen, it changes the probability of the thing you're trying to find happening. We write this by doing this. It's going to be something along these lines, and it's a little normal probability and then a line between two probabilities. B is what's given to you, okay? And we're trying to find the probability of A in this case. And here's the formula, okay? This reads probability of A given B. Whatever you're given, here's a little tip for how to set up your formula if you're stuck. Whatever you're given goes in the denominator, okay? And then numerator finding a probability of A and B, okay? Same story here. Denominator is probability of A. If you're following along with the guided notes, we'll go back to this lovely table here in a little bit. But if you want to copy us down and fill out your box, go for it. We'll get back to it momentarily. So tree diagram. So this is a problem I'll let you read on your own, but would greatly benefit from a tree diagram. Okay, and you might wonder what is that? Well, when there's multiple events where the cause of one changes the probability of another, um, that's where a tree diagram will be beneficial. So I'm going to go down below here and make one for us. Okay, and then I'll answer these two questions here: the probability of randomly selected athlete tests positive, and suppose that the chosen athlete tests positive. What's the probability? So by doing this tree diagram, we'll have a much easier time. Here's what the tree diagram would look like. Okay, so 10% of the athletes took steroids, and that means 90% didn't, right? It's whatever leftover is. As the problem said, test is accurate 95% of the time when the athlete has taken steroids. That means if its accuracy is 95%, positive test would be 95%, and then negative test would be 0.05%. And then it's 97% accurate when the athlete hasn't taken steroids. So it's accurate. When the athlete didn't take steroids, 97% accuracy. The rest of the 100% goes to the plus. So let's answer these questions. What's the probability the randomly selected athlete tests positive? So athletes testing positive, there are two different scenarios. I'm going to highlight this in red. So test positive is right here and right here. Okay, so what we're going to do, the probability of the top event happening is this times this, right? Which will get you 0.095. And then the probability of these two things happening is going to be 0.027. Add those up, and you're going to get to so about 12.2% would be your answer to the first part, the probability of randomly selected athlete tests positive. Now the second question, suppose that chosen athlete tests positive. So given, when you see that you're in your head, you're saying given. So if your given is test positive, that means our denominator is what we just found. What's the probability they actually use steroids? Okay, so if they use steroids, it was this times this, right? So that's going to be your numerator. So what we found first is our numerator, 0.05. That is your answer to the second part. First part was 0.122, and the other one was what we just found. Another tree diagram problem, yeah. So, 10,000 switches, 1,000 are bad. Okay. Uh, so if I'm not given a percent right away, I'm just gonna use fractions. Okay. So I'm just gonna go good switch, bad switch. The reason I chose this problem and then that we need to do a problem like this is because when it's the same event happening twice, but you're losing one less item, right? So, like for the first event, you have 10,000 switches, 9,000 work, 1,000 don't, right? Um, so after one of them worked, there's one less switch and one less one that worked. So you go down to 8,999, and there's still 1,000 that don't work. And over here, you got doesn't work, one less one that doesn't work, right? So it's instead of being 1,000, um, you're gonna have 999, and this should have been 9,000 right here. My bad. Uh, so that's what your tree diagram will look. So what's the probability that both switches are defective? So that means we're right here. We use different colors so we can point it out. So that means it doesn't work, doesn't work. Both switches don't work. So it'd be the first fraction times the second fraction in order to get both defective, which will get you an answer of 0.009991. So, definition of independent events. If two events A and B are independent, if the occurrence of one event does not change the probability that the other event will happen. Um, we can, if we write this as a conditional, probability of A given B happening is just simply the probability of A because one does not affect the other. Okay. Also, pretty much what we did in one of these problems. If you're trying to find the probability of A and B, you just simply multiply two events, which is what we did in all these problems, right? We multiplied. Okay, so we did examples of the multiplication rule. Now, independent events, if we go back up, whether the pizzas here at Mike's Pizza Shop were thick or thin crust or mushroom no mushrooms, did not, they're independent of one another, right? One does not affect the other. But we can, in this case, since we know more details, better predict because we knew one or the other. And that's everything. Appreciate you watching, and we'll see you in class. Bye bye.